Okay, so now we have two ways to represent a complex number. One is in Cartesian form, x plus iy, and one is by using the modulus of the complex number and the argument of the complex number. And somehow we want to combine these to be able to represent the complex number in something that we're going to call polar form and then in complex exponential form. So here's my picture, and my complex number z is still sitting up here in the upper quadrant, and my z in this example is x plus iy. And so we've got all of those things noted on this picture now. So the real part is x, the imaginary part has coordinate y, gives us a right angle triangle here. The angle that it makes with the positive real axis is theta, and the distance from the origin to the complex number is the modulus of z, and I've just called it r here. Okay, so from the diagram, we know that, remember from our work on trigonometry, the cosine of theta is equal to the adjacent side over the hypotenuse, and the sine of the angle theta is equal to the opposite side over the hypotenuse. So on our picture, the adjacent side is x, and the hypotenuse is r. So I can write cos theta as x over r, and I can write sine theta as the opposite of the hypotenuse, and in our picture the opposite is y and the hypotenuse is r. So now I've got theta, x and r represented together, and theta, y and r in this equation as well. So I can rearrange these two equations to write x in terms of r and theta, and I can write y in terms of r and theta. So what I'm going to do now is I'm going to use these relationships to replace x and y in the Cartesian form. So we're looking at the equation that we had before, z equals x plus iy, but we saw that x could be written as r cos theta and y can be written as r sine theta. And so if I just substitute x for r cos theta and y for r sine theta, then I get something called the polar form. And the polar form of a complex number z looks like this. So z is equal to r, so I've just taken the r out the front, cos theta plus I sine theta. So now I've represented my complex number in terms of the modulus r and the argument theta. And this is called polar form. Okay, so let's express the following complex numbers in polar form. So we might just do this one, and I'll leave that one for you to do by yourself before Thursday. Okay, so here we've got our complex number z equals square root of 3 plus I. And we want to write that in polar form. So to write it in polar form, we have to work the modulus of z, and we have to work out the argument of z. So let's recall what those definitions are. So mod z is equal to the square root of x squared plus y squared. So in our case, that's just the square root of, well, x is root 3, and y is just the coefficient of I, which is 1. So this is equal to the square root of 3 plus 1, which is 4. And so the square root of 4 is just 2. So our modulus of z is 2, and the argument of z is theta, where tan theta equals y on x. Now again, let's draw a picture so we know what quadrant we're in. So it's root 3 in the real, along the real axis, and it's 1 unit up the imaginary axis. So my complex number again is in the first quadrant in this example. So tan theta equals the y coefficient is just 1 and the x coefficient is root 3. So tan theta equals 1 on root 3. Let's go back to our favourite triangle. So remember, pi on 3 is opposite the root 3 side, 1 and 2 along the hypotenuse. And this angle then is pi on 6. And we want the angle that has the opposite over adjacent as 1 over root 3. So 1 is opposite pi on 6, root 3 is adjacent to pi on 6, so tan of pi on 6 is 1 over root 3. So it looks like the argument of z is pi on 6. So writing z in polar form is z equals r cos theta plus I sine theta. So in this example we have z equals 2 cos of pi on 6 plus I sine of pi on 6. And that's our complex number z in polar form. Okay, so now we know how to write a complex number in polar form. It's r times cos theta plus I sine theta, where r is the modulus of z and the argument of z is equal to theta. So we're going to write that in a slightly more compact version by using this function called the complex exponential function. And the complex exponential function, e to the I theta, is defined to be cos theta plus I sine theta. So the exponential function has as its domain the purely imaginary numbers, so I times a real number, and the range of the complex exponential function is the complex numbers. We're not going to use it much in this course, but you'll see this more if you do a complex analysis. In this course, for us, it gives a really convenient way to write the complex number in exponential polar form. So instead of writing it in this way, z equals r times cos theta plus I sine theta, you'll notice that all of this stuff in the bracket is just what we define to be e to the I theta. So we can write our complex number as z equals r e to the I theta, where r is the modulus of z and theta equals the argument of z. Let me write that so you can read it. Okay, so let's do an example using the exponential polar form. So we've got our our complex number z written in Cartesian form, and we want to write it in exponential polar form. So we still have to figure out what the modulus of z is, we have to figure out what the argument of z is, and then we're going to write this as z equals, let me call that r, and we'll call that theta, r e to the I theta. Okay? So let's have a look. So our modulus of z, remember, is the square root of x squared plus y squared. So for us, it's the square root of minus 2 squared plus 2 root 3 squared. So this is equal to the square root of 4 plus 4 times 3. So it's the square root of 4 plus 12, which is root 16. So that gives us 4. And remember, draw yourself a little diagram. So now our complex number is minus 2 on the real axis, and it's 2 root 3 on the imaginary axis. So the complex number here this time is in the second quadrant. So we'll have to be a little bit careful when we're finding the angle theta. Okay, so the argument of the complex number is theta, where tan theta equals y over x. So our y now is 2 root 3, and our x is minus 2, so this is going to be minus root 3. Okay, so now we have to figure out what our angle theta is, given that tan theta is equal to minus root 3. We're still in the second quadrant though, so we have to be careful. We can't write this as arctan, because remember, arctan is only defined from between minus pi on 2 and pi on 2, so it's only defined on this side of the axis. Okay, so let's work out what our angle theta is. So our complex number is the point here z, and the angle theta that we're looking for is that one right there. So if you think about forming the similar triangles, you'll find out that if that angle is pi on 3, I'll just write it down here because it doesn't fit, then the opposite side is 2 root 3, and the adjacent side is minus 2, and so that gives us tan theta equals minus 3. So this angle is pi on 3, but we're in the second quadrant, so our angle theta is equal to 2 pi on 3, because it's going to be pi minus pi on 3, that angle there. So theta is equal to 2 pi on 3, so that means our complex number z is equal to re to the I theta. R is just 4, and theta is 2 pi on 3. So that's exponential polar form. Okay, so we've been through quite a bit of material now, so it might be a good idea for you to take a bit of a break. Do the next examples in the book. So there's some homework problems and examples following this slide in your notes. And it would also be good if you could try some questions from the problem sheet book. So we're working on topic 3, and you could do down to the end of question 14 out of that book pretty well now, I think. Have a go at some of the examples so that you get a good feel for what's going on. And in the next video, we're going to start talking about some properties of the complex exponential. So have fun with complex numbers.